Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So in our discussion today, we are going to look at entropy changes in a spontaneous process. And of course, this is going to be in consideration of an ideal gas, which we are going to consider as our system. So in this case, I'm going to have this one. This is going to be an ideal gas as a system. And of course, this other space is going to tell what we refer to as the surrounding. So basically, it's going to be our system and the surrounding given as such. And from the second law of thermodynamics, we have said that the spontaneous processes are basically going to be thermodynamically reversible processes. And for an ideal gas from the kinetic molecular theory, we stated that there are going to be no attraction forces between the molecules. Hence, we can be able to conclude that there's going to be no heat absorbed or evolved in this specific process. Therefore, there's in this specific scenario, if we look at the ideal gas and the surrounding, there's not going to be any heat that's going to be removed or supplied from the surrounding. Hence, the entropy of the surrounding, this specific point, therefore, is going to be remaining unchanged. And of course, this can be given in this specific form. The delta S over the surrounding is going to remain unchanged. But if you consider the entropy of the system in this particular case, the gas is going to be increasing in volume. Therefore, we are going to experience the delta V given as such. And of course, this is going to be the change in temperature, or rather the change in volume of this specific gas that is going to be experiencing expansion. Remember, we said that this particular gas is going to be expanding in a vacuum. Therefore, there's going to be a net change in volume that is going to be depicted by the delta V given as such. So if this particular aspect of the entropy is going to depend on volume and pressure of the system, and of course we're going to see that this aspect of volume for changing from V, or rather from V1 to V2, or V2 to V1, which is going to be the delta V, and therefore we're going to experience some kind of entropy in the system that is going to be given in terms of delta S is equivalent to R, the natural log of V2 over V1. Of course, we've done this one in our previous videos. So I'm going to put a link in the description box so that we can be able to see how we have achieved this aspect of entropy from this specific representation. So therefore, the entropy change of this specific surrounding, as I've said, is going to be given as 0. And therefore, from this comparison between the system and the surrounding, we can be able to, or we can give a total change in entropy using this specific formula, whereby we have a change in entropy of the system and change in entropy of the surrounding equivalent to R, the natural log of V2 over V1 given as such. So this is going to be the total change in entropy of that specific system. And in this case, since the process is, of course, going to be expansion of this specific gas, this is going to be accompanied by a positive change in volume, which is V2 is greater than V1. Therefore, the value for entropy is going to be a positive 1. Therefore, we can conclude that of course, the state of the spontaneous reaction, spontaneous process is going to be an isothermal expansion. And we had considered this specific expansion at the temperature, let's say this one given as T1. And of course, it's going to be an isothermal expansion of an ideal gas that's going to be accompanied by increase in entropy given as such. And of course, we have mentioned that for reversible changes, the entropy of the system is going to be remaining unchanged. And therefore, we are going to, of course, expect for a reversible process. Remember, we are saying that for spontaneous processes, these are thermodynamically reversible processes. So we can be able to contrast this one with a reversible process, whereby we're going to see that for a reversible process, the entropy of the system is going to be given as equals or greater than 0 given as such. And this is going to have an implication, of course, of the consideration of entropy changes in either a spontaneous or non-spontaneous process given as such. So in summary form, I've said that the entropy changes in a spontaneous process can be considered using this specific system and the surrounding, whereby we have said that in this specific system, the gas is going to be, of course, expanding into the vacuum of a space at a constant temperature T1. And of course, we are going to see that from this ideal gas, we have decided that one of the characteristic description from the kinetic molecular theory is that this ideal gas is going to experience no forces of attraction between molecules. Therefore, we are going to consider that there's not going to be any heat that is going to be taken in or out of this particular process as I've mentioned. So therefore, the heat that is going to be supplied is not going to be supplied as I've mentioned. And of course, the entropy of this specific system surrounding is going to remain unchanged. Therefore, I gave it as a delta S equivalent to 0. And of course, we said that we can be able to consider the concept of entropy of this particular system that is consisting of a gas that is expanding. And of course, that one has an implication that its volume is going to change from V2, or rather from V1 to V2, given as such. So therefore, in consideration of the constant temperature and pressure, we can be able to describe this specific aspect of entropy using this particular formula, which I had said I'm going to put a link in the description box giving a specific derivation of this specific formula that we're going to consider in this specific case, given as a delta S is equivalent to R natural log over V2 over V1. And of course, therefore, since the entropy of the surrounding is 0, we can give the general form of the change in entropy of this specific surrounding system using delta S, which is the entropy of the system plus the entropy of the surrounding, giving us the natural log over R, the natural log over V2 of V1. And therefore, we're going to see that this value is going to be positive since for expansion V2 is greater than V1. And we can be able to, or we can contrast that specific product of entropy together with an, of course, a reversible change, where the entropy of the system plus the surrounding is going to remain unchanged, and it's going to be given as a delta S is greater than or equivalent to 0, given as such. So that's the comparison between enthalpy changes in a spontaneous and non-spontaneous process. And specifically for our case, this is going to be the scenario we are going to consider a spontaneous process in that specific aspect. So that is it for now, guys. Kindly check our description boxes for various links and subscribe to our channel so that we can be getting more updates on these specific topics under thermochemistry and physics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.